So the next talk is Andreas, who's going to tell us about cavity optometrics. Hopefully I got that right.
All right, let me thank the organizers for giving me the chance to give you a bit of a flavor what's happening in my group here at the Cavendish, where I'm a Royal Society URF. Here's my group. Here are the funding agencies supporting our work. And before I start, I will just give you the big picture. What we are interested in is looking at different platforms which will be important for future quantum science and technology. Looking back, the last century was really about where physics changed the world in various ways, thinking about bringing up new electronics, materials, lasers, and imaging. And what we think is looking forward that we can do it again, that now quantum coherence can play a major role in the 21st century in the so-called second quantum revolution. So that could change both as we are thinking about sensing, how we make secure communication, how we simulate many body systems, and eventually leads to quantum computers. So to actually make this happen, to achieve this goal, what we need is to create, control, and exploit quantum coherence in a larger scale. And we've been looking at various platforms to make this happen. This is called atoms. This is mechanical systems, where I will talk more about in a second. Semiconductor nanowires, superconducting circuits, diamond, quantum dots, etc., magnetic systems. And so I will focus now for the next 10 minutes here on this structure optomechanics and give you two ideas what we've looked at recently. So what's cavity optomechanics about? Cavity optomechanics is about coupling mechanical motion to a cavity mode. So you can think about a cavity like this here, two mirrors, and one of the end mirrors can move. It's mechanically compliant. And by changing its position, it's tuning the cavity frequency. So here's the simplest model you can write down. There's one mechanical mode here, which is the mechanical motion of this object here with the frequency omega m. And this is the cavity mode, cavity frequency omega c, and that depends parametrically on the position of the end mirror. So for many examples, this can be Taylor expanded, and you can think about it as a linear relationship here, and then you end up with such an interaction Hamiltonian between the mechanical oscillator and the cavity field operator here. So that's one way to think about it. You can think about the other way. What does happen to the mechanics? And you can think about what's the force which the photons impinge onto the mirror, and then you find its proportion to the number of photons. This is the physics of radiation pressure. So the photons inside bounce against it, and they push the end mirror. This is something which happens in a lot of different systems all around the world in the various labs. This is maybe the one closest to the theorist picture, where there's a micromirror, but there's other things, other structures which are doing this in the optical domain, say photonic crystals, and also in the microwave domain, even for single trapped glass beads, and on the other end of the scale, LIGO, as like the kilogram and hertz variant of this idea. At Cambridge, we don't have one of those experiments, but we have several which are related. One Jeremy was talking about earlier, which uses a single molecule, and then we have here color centers which are tuned by strain, and also collective not mechanical but magnetic interactions which can be coupled to light and microwaves. What is this field about? Well, for a decade, people have tried to reach to the ground state. We know how to do that now. We know how to achieve strong coupling. So now that we have this in the lab, what are the possibilities? Some groups are focusing on something very fundamental, trying to do gravitational decoherence. Some are coupling to various exotic degrees of freedom, such as other magnetic structures. Others are looking at extending from a few modes to many mode system. I will say a word about this. And yet others are trying to make use of this structure in the context of quantum technology. This work about quantum technology has been supported by the EU, by this FAT Proactive, and I will give you one flavor of such a project now. Very often you have the situation that you have a signal source out there and you want to amplify a very small signal. So what ends up is you want that the signal over here reaches your detector and your amplifier is strongly amplified. What we don't want is that the noise from this side reaches your quantum source. So you need in between something which is non-reciprocal, which lets something through but not back. In particular, a structure we're thinking about is this here, which is superconducting circuits, a good platform for quantum computing. Typically what we're using actually now is IGIG. So inside you have these circulators and isolators which break Lorentz reciprocity with optomagnetic effects. However, this is really macroscopic and bulky and lossy, and we like to replace this by something on-chip reconfigurable. And there's a whole field trying to achieve this. I will show how to do this with mechanics. So what we do is here in cooperation with EPFL, we've been looking at a structure which is vibrating. You have a capacitance which depends parametrically on the position of this capacitor plate, which has the same Hamiltonian I showed you before. And then we're using 2 cavities, 2 mechanics, and 4 drive tones. And what we achieve is, I won't go through the details here, what we achieve is that we're coupling the mechanical motion to the optical fluctuations, and we end up with a structure which looks like this. These are the 2 mechanical modes and 2 optical modes, microwave modes, which are coupled in a ring structure. So we call this optomechanical plaquette, and there's one gauge invariant phase in this problem here. It's like hopping of a particle on a ring, which is threaded by a magnetic flux. So we have something where there's an artificial magnetic field which is created by this driving. And now we can play with the artificial magnetic field together with dissipation, and that's how we can break the reversal between backwards and forwards. How is this done? This is when I remove the link, then everything's reciprocal. This is the S matrix of the object linking input to output. It is the same for 1 to 2 and from 1 to 2 and 2 to 1. It's reciprocal. Now I close the link, then I can play with interference between the 2 paths going up here and below here. And crucially, there's a phase in between these two matrix elements, which are changed by the flux through the ring. And then I can move this number here away from 1, which signifies that it's non-reciprocal. So we can have constructive interference in one direction, and we can have destructive interference in the other. And there is your window of non-reciprocity here, between here's 1 and here's 0. This is something we took to the lab at EPFL. So this is the ideal structure here of an isolator. So we took it to the lab of Tobias Kippenberg, and this is what we get. So we can achieve, with tuning this phase between the drives, you can achieve the reciprocal and the non-reciprocity one way and non-reciprocal way the other way. So you can make the structure, and it's really based on mechanical motion of this tiny object, and it can achieve that microwaves can only move in one way or tunable the other way. And I think this is quite remarkable. This is really something oscillate at megahertz frequency and can be cooled down to the quantum regime operating close to 0 effective temperature. We've developed this further and looked not only into isolation, but also into directional amplifier, which is quantum limited. And more recently, we looked into how to move this, the whole story, what I just told you about this interference and therefore directional transport, how to move this from bosons to the fermionic degrees of freedom. If I have the time, then I will add 2 more sentences that this structure of mechanical motion in the quantum regime also offers something of new physics. So that relates to one of the topics here, relates back to Christian Huygens, which is related to the phenomena of synchronization. Synchronization is something where you can think of pictorially as metronomic clocks. So you have 2 metronomes like here, set to different speeds. You start to couple them, they come to a new speed, and then you can draw such a diagram here where you find that although they were set to different speeds initially under coupling, they have changed their frequencies so they're now in sync. So what has this to do with what I just told you before about the cavity optomechanics? Well, you can think about structures which contain 2 or more of these degrees of freedom and are mechanically coupled. Then you can excite the system into self-sustained motion by driving above the resonance frequency of the cavity. If you overcome the internal dissipation, self-sustained oscillations start, the system acts like a laser, and then you can ask, what is a synchronization in the quantum regime? Here's a structure where this can be actually looked at. This is an optomechanical crystal. There's many modes here which are co-localized, many optical and mechanical modes which are co-localized. So you end up with a many-body problem here, which is locally coupled between mechanical motion and optical motion. So in such a scenario, you can ask many questions, including question of synchronization, but also new localization effects and topological phase of light and sound. We have started to explore this a little bit in various toy situations, not looking at the full system yet in these papers here. And that brings me to the end, where I want to show you that cavity optomechanics is one of the platforms which moves forward this agenda of quantum science and technology. It's one of the structures which can be of use there. I showed you one example how this structure can be important for near-term quantum technologies, for instance, this isolator business, and it also offers the potential for new quantum physics, as for instance, this synchronization. Thank you very much for your attention.
Thanks, Andreas. Some very interesting stuff there. So any questions? Joanna. I thought that was Chris gone.
Sorry. This is a slightly tangential question, but as a theorist, you're clearly working with a lot of experimental groups here, which is really exciting to see a talk that puts them both together. Can you talk a little bit about how that link works and how you ensure that that link works? Because some of these labs you're working with are not physically here in Cambridge. Could you just say a few words about that?
You mean, yes. Well, I mean, the, well, I mean, this is personal connection from a personal network within in a field, right? So, I mean, how does the interaction work? I mean, I think as many of us are working, non-locally with experiments and theorists which are not present in the same location, but I mean, nowadays with Skype and conference and so on, that works pretty well, as long as you're good and well in touch. So, yeah, this is, I mean, to be explicit, one thing which actually is maybe of use is, I was previously a postdoc in Switzerland, and there's a very good network which is QSIT, which brings together all the quantum science in Switzerland, and I still benefit a lot from being part of that in the past. So this collaboration was set up back in that time. So I think maybe that's one way to answer that question.
Okay, thank you.
Coupling human interactions is much more difficult than the quantum regime. So any other questions? Henning again.
One question about the optomechanical cavity on a chip you showed. If you implement this on a chip, isn't there a problem with noise feeding back onto other systems you have on the chip? Because if you move the mirror mechanically, I would expect that it also leads to decoherence in other systems which can be connected to this on the chip.
Yes, there's definitely coupling from. I mean, there's finite decoherence in the problem, and so the mechanical motion is damped. It is surprisingly little damped, and it can oscillate for actually, the typical quality factors are in the 10,000s, 100,000s, so it's pretty well isolated. And that takes everything into account. I mean, that's like the effective thing you actually see in ring down.
I'm thinking about if you were to embed it in a quantum computer, for example, you would also not want to feed mechanical noise into systems which are nearby on the chip.
I see. Yes, you would have to worry about good mechanical isolation, but that's what you want anyway. These are yes. So okay. There's always something happening on the chip anyway. Yes.
Okay. Thank you.
Okay. I think in the interest of time, we should move on. So let's thank Andreas again. Yep.